Hello and welcome to Lecture 3 of Electric Charges and Forces in PHYS 1201. And in this lecture we're going to meet what is arguably the basis of all of the theory of electricity, and it's called Coulomb's law. It deals with how strong forces are between charged objects. So from the last two lectures, and especially 2 lectures ago, there are already a bunch of things that we've been able to demonstrate about electrical forces. And so any equation we write down that describes electrical forces has to produce all of the results that we've already seen. So first of all, for opposite charges, electrical forces are attractive. And for similar charges, they're repulsive. Now notice I'm drawing 2 objects, and so this is an interaction pair. The one exerts a force on the other, and the second one exerts a force back on the first, and they are in opposite directions and equal in magnitude. So that still applies. Newton's third law still works. So any equation we have for electrical forces also has to be consistent with Newton's third law. The next thing we know is that if we increase the charge on an object, then it exerts a stronger electrical force. But again, Newton's third law tells us it will also feel a stronger electrical force. So the electrical force has to depend both on the charge on the object that exerts it and on the charge on the object that is feeling the force. And finally, we know that the electrical force decreases in strength when we move objects farther apart. An idea we're going to make quite a bit of use of is the idea of a point charge. And it's actually fairly familiar to you from PHYS 1101 because there we were consistently talking about objects as point masses. So this is a similar idea. We're thinking of a particle. So in other words, a thing that has no size, it occupies no volume, it's concentrated at a point. And all of the charge of it is concentrated at that point. And this seems like one of these weird idealizations, but in fact, experimentally, as far as we can tell, electrons are actually point charges. And various other subatomic particles are as well, although I'll say protons aren't. Turns out protons aren't point charges, but they're so tiny that for our purposes, you can certainly treat them as point charges. Now, the things you actually touch on a day-to-day basis are nothing like point charges. Rods, spheres, plates, and things like that, which are the sorts of things we're going to talk about most often in this course, are not point charges. And so you should be aware that the laws we use to calculate forces due to point charges don't apply to those things. However, those things are made out of point charges, so in principle you can derive the forces that they exert on each other from the laws that apply to point charges. We won't see how to do that, though. So now we come to Coulomb's law. And I'll just reiterate, it only applies to point charges and to uniformly charged spheres. And so let's talk about 2 spheres, or they could be point charges, and they have amounts of charge on them. And we haven't talked about the units we use to measure charge. We'll get to that. But let's just say they are quantities Q1, Q2, and we'll tend to use Q to represent charge. And they're separated by some distance r. And notice how I've drawn that. It means the center-to-center distances of the spheres. So these are our quantities. They're going to exert some electrical forces on each other, and these forces we know have to depend on how much charge is on each object, and they have to depend on how far apart the objects are. Well, if you increase the charge on one object, then the force on both increases, which means the electrical force has to depend on both of the charges. And it turns out it just depends on the product of them. Now, notice I've written no vector symbol on here, and so I'm talking about a magnitude of the electrical force. And so I'm taking absolute values here so that we're only talking about the sizes of these charges. We're dropping all signs. And throughout this course, we're going to tend to do this. We're going to drop all the signs, use Coulomb's law to calculate magnitudes, and then we're going to use our knowledge of whether the charges are opposite or similar to decide which direction the forces point. Next, it has to decrease with distance. Well, that means you're going to divide by some power of distance. And it could be r squared, who knows? Well, who knows? Physicists do, because experiment tells us that it goes as 1 over r squared. So for example, if you double the distance between the two objects, the force that they exert on each other decreases by a factor of 4. And finally, this is still only going as, or proportional to make it equal, you need a proportionality constant. And that's basically defining how your units work. And so this constant K is sometimes called Coulomb's constant, and it is this big number, 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. And you don't really know what a Coulomb is yet. It's come up briefly when I was talking about the fundamental charge unit, but one of the first things we're going to do is establish about how big a Coulomb is. It's good to have an idea of what a Coulomb of charge means. But if you check these units, you see Newton meters squared per Coulomb squared, you're multiplying by Coulomb squared, and so the Coulombs all cancel out, and you're dividing by this distance in meters, and so the meters all cancel out, and you're left with newtons, as you must. So the problem with a unit like a Coulomb, which is what we use to measure charge, is that it's sort of insubstantial. You have no direct experience of it. A meter is easy. You can hold a meter stick in your hand and you can look at it and see how long a meter is. A second, just watch the hand go on a clock or watch the seconds tick by on a digital clock and you know how long a second is. A kilogram, you can easily pick up an object with a mass of a kilogram and feel what a kilogram is. But you have no real direct access to quantities of charge. You can't see it, you can't hold it in your hand and feel it. All you can do is observe its effect. But we've done that, so let's use that. In the first lecture of this unit, you saw 2 ping pong balls covered in aluminum foil standing out from each other at an angle because they were repelling each other. And they should have had about the same charge on them because they were sharing their charge. Charge had been transferred onto one and they had then shared their charge. And so we can use that to actually figure out how much charge was on them. So 3 grams is about right for a ping pong ball, especially if it's been covered in aluminum foil. 5 degrees is a reasonable estimate. I don't know whether the ones in that video were standing out 5 degrees from each other, but it's about the right size. We certainly could make 2 ping pong balls stand out from each other at 5 degrees. The radius of a ping pong ball is 2 centimeters, and so if their edge to edge is 1 centimeter, then the center to center ends up being 5 centimeters. And so from this we can figure out how large the charge is on each of these balls. So let's think about 1 ping pong ball. And you know what to do. We're talking about forces. We'd better draw a free body diagram. So some of this is simple, and I'm just going to go ahead and draw it. There's our free body diagram of our ping pong ball, and we know that this ping pong ball is standing stationary, so we'll say F net is 0. There's a tension here, which is directed at a 5-degree angle from the vertical. There's a weight, and the new thing here is this electrical force. So we know how to analyze this situation. We'd better define some axes and take our sums of forces. So I'm just going to write them out, and you should too, and make sure you remember how this works. All right, so far everything here is something you could have done from PHYS 1101. Although, there are a few tricky bits. There's a little bit of trig here, and in the end, there was a double substitution to get rid of t and put it in here and solve for the electrical force. And it turns out that it ends up being mg tan theta. And we know theta and we know mg, so we can certainly solve for Fe. Now is the only new thing. We know how to write Fe. It's K Q, right? Q of the charge that's exerting the force times Q of the charge that's feeling it, but that's just Q squared here over our R squared, and that equals our mg tan theta. And so at last we can solve for Q. So we get this answer of 27 nanocoulombs. Small. The Coulomb is a big unit. And so now you have an idea that with objects like this, where we're just charging a few things by rubbing and maybe transferring some charge around, you have a tendency to get charges of the order of nanocoulombs. Let's calculate the total force that these two charges, 2 and 3, exert on this charge 1. And I'm going to do this really fast because I'm really just reminding you that forces are vectors and you have to add them together as vectors. So I've already found the magnitudes of these forces over here, and you should check these numbers. And if you don't come up with the same as me, I'll remind you, nano is times 10 to the negative 9. Be careful that the distances are in centimeters. Watch out for Pythagoras when you're calculating this distance here, and it should all come out fine. And now the forces on Q1 are going to be an attractive force towards Q2, and so that's up, and a repulsive force from Q3, so that's down this way, and that one is directed at a 45-degree angle. And so now you could calculate your Fx, the total x component of forces, by simply taking negative F3 cos 45 degrees, and you can calculate that, and you can get your total Fy by just taking your F2 minus F3 sine 45 degrees, and you can calculate that. And that's all there is to it. It's just vectors as we learned it last term in 1101. To finish off, I'm just going to reiterate a limitation of what we've just learned. Let's say we have a ball here with some charge Q1 on it. And over here we have a big flat plate, and it's got a charge Q2 on it, and they're separated by some distance r. Now you may be really tempted to say, oh, the force that 1 exerts on 2 is going to be from Coulomb's law, right? Wrong. Wrong. Because Coulomb's law only applies to spheres and point charges. This is a plate. Coulomb's law doesn't apply. You cannot calculate this force using Coulomb's law. We'll learn how to do it, but it's with a method we haven't seen yet.